Okay, we're in chapter 3. The start of chapter 3 deals with solving systems of linear equations. Section 1, we're going to solve these equations by graphing. Systems of linear equations are equations that consist of two or more equations. Um, Two variables are usually in occurrence x and y, and they're written as the following, kind of like this in standard form, where it's ax plus by equals c, and the second equation is also in standard form, which is dx plus ey equals f. Those are just variables in the general form. Um, to find a solution for a system, you're going to get an ordered pair of x and y that satisfies both equations. So if you do end up finding a solution while graphing, it's where both lines intersect. That's what is considered the solution for a particular problem. And I can assure you that sometimes graphing can be difficult, especially by hand. It's a lot more accurate if you do it with some type of graphing calculator or some other use of technology. But today, I want you to be able to see what it looks like when you graph it, um, the physical solution that you would get. So for this, I sometimes human error can be occurrence. So what I want you to do is when you find a solution that you can estimate, I want you to check that solution algebraically to see if it works. I'll show you what that is. So for example A, I have 3x plus 2y equals negative 4 and x plus 3y equals 1. So I want to be able to draw a line for this, for these equations. In order to do that, I need to get it in a slope-intercept form, which is y equals mx plus b. I need to find my y-intercept. I need to find my slope. So what I'm going to do is I'm going to solve for y for the first equation. First off, I'm going to subtract 3x to both sides. So I got 2y equals negative 3x minus 4. To get y by itself, I'm going to divide both sides by 2. So I'm dividing each value by 2. So I get y equals negative 3 halves x minus 2. So this one, the first equation, is in slope-intercept form. Dealing with the second equation, I'm going to subtract x to both sides. So now I have 3y equals negative x plus 1. Now I need to divide 3 to both sides. So now I have y equals negative 1/3 x plus 1/3. Okay, so now that I have both of those, now I can graph them. So I'm going to graph my first equation. My first equation tells me that my y-intercept is at negative 2, so I'm going to plot at negative 2. I got a slope of negative 3, so I can either go down 3, 1, 2, 3, and to the right 2, plot it there, or I can go up 3 to the left 2. As you can see, those three lines will connect to give us a line. So I'm going to try to see if I can make a line here as best I can. It connects. Try to just extend it here. So now going to the second line, I'm going to go, my y-intercept is 1/3, so it's probably somewhere right around here. And my slope is negative 1/3, so I can go down 1 to the right 3, 1, 2, 3. Or I could go up 1 and to the left 3, 1, 2, 3. So something like that. Gonna make my line, do the best I can, because it's estimating. And that looks like what our line should be. And as you notice, I have an intersection right at this location. And I estimate that is about at -2 comma 1. So that is my estimation where I think my solution should be. So what I need to do in order to prove that that number is correctly, I need to plug them back into the original equation to see if the statements are true. So I'm going to plug in -2 in for x and 1 in for y and see if I get a true statement. So I'm going to deal with the first equation. 3 times a -2 gives me a -6, plus 2 times 1 gives me 2. Does that equal -4? Yes, it does. So that checks out. And now I need to see if it works for the other one. It must work in both equations for the system order and pair to be a solution for both systems. Let's see here. So I got -2 plus 3. Does that equal 1? Yes, it does. So it satisfies both equations, so I can say with full confidence that my solution here is -2 comma 1. Same thing here. We're going to solve for y. So I'm going to subtract 4x to both sides. So I got y equals 4x, I'm sorry, -4x plus 8. Second one, I'm going to subtract 2x to both sides. So I got -3y equals -2x plus 18. I need to subtract -3 to both sides. So that's with every value there. So I got y equals, since it's two negatives, it's 2/3 x minus 6. So these are my two systems that are, or these are my two equations, that are in slope-intercept form. So y-intercept for the first one is 8, and my slope is -4. So I'm going to go 1, 2, 3, 4 down, and 1 unit to the right. So with that, I'm going to draw my line. Doing the best I can to stay within the points. It can be tough, especially with human error. So the next one is negative, my y-intercept is -6. So I'm going to go 1, 2, 3, 4, 5, 6. And my slope is 2/3. So I can go 1, 2, 1, 2, 3. So right about there. And draw my line. Something like that. And look something like that. So again, I found another intersection. It's somewhere right around here. So it looks like it's at 1, 2, 3, comma 1, 2, 3, 4. So it's -4. So that's my ordered, or that's my solution for my ordered pair, in an estimation. So in order to prove that, I must do it algebraically. So I'm going to substitute in 3 in for x and -4 in for y. So I have 12 for the first one plus -4. Will that give me +8? Yes, it will. Second one, I have 6 minus -12. Will that equal 18? Well, this becomes plus plus, and 6 plus 12 will equal 18. So that checks out too. So my solution checks out for this particular situation. Also in this section, we're going to deal with classifications of systems that we have: consistent, inconsistent, independent, and dependent. A consistent system means that the system has at least one solution. It can have more than one solution, but it has to have at least one. An inconsistent system has no solutions. What that means is our two systems will have the same slope but different y-intercepts, so that would define that those two lines are parallel. And since they're parallel, there's no intersection, seeing that there's no solution. An independent system is a consistent system because it has at least one solution, but it has exactly one solution. So an independent system only occurs when the two lines intersect at just one point. And a dependent is a consistent system, but it has infinitely many solutions. So what it basically boils down to, when you simplify both equations in slope-intercept form, they should be the exact same line, and they'll overlap each other. That's how it gets infinitely many solutions. So when you're looking at the relationships of these classifications, if you have exactly one solution, it looks something like this, where you have a line here, and then you have a line here, and then you have an exactly one solution located here. If you have exactly one solution, those lines can be classified as a consistent and an independent system. If they have infinitely many, that means you're just going to show, it's basically going to show up as one line because both lines overlap one another. And those will be classified as consistent and dependent. If I have no solution, that means that my lines are parallel, which means they will not intersect. So this is classified as an inconsistent system. For these examples, I want you to solve the system. Then I want you to classify whether they're consistent and independent, consistent and dependent, or inconsistent. So here, I'm going to do what we did in the previous examples. I want to get it in slope-intercept form. So for the first one, I'm going to subtract 6x to both sides. So I got 2y equals negative 6x plus 8. Next, I'm going to divide both sides by negative 2. So I got y equals 3x minus 4. So that's my first one. The second one, I'm going to subtract 3x to both sides, so I got negative y equals negative 3x plus 4. I have a negative y, so I need to divide by negative 1 to both sides, so I have y equals positive 3x minus 4. I notice that both of these equations are exactly the same. So since they're exactly the same, we can conclude that this is going to have infinitely many solutions. I don't even have to graph it, I already know that. Probably spelled infinitely wrong, sorry. I think there's an I there somewhere. But if I'm going to classify this, if I know that it has infinitely many, I can look up here and infinitely many has a consistent and dependent system. So that's the classification for example A. If I go to example B, I'm going to, again, solve for y. So I'm going to add 4x to both sides. So y equals 4x plus 5. So I'm done with that one. Going to the second one, I'm going to add 8x to both sides. So I have 2y equals 8x plus 14. Dividing both sides by 2. I got y equals 4x plus 7. Now, I notice that they have the same slope, different y-intercept. So what that's telling me is that these things are going to be parallel. So if they're going to be parallel, that means they don't intersect. So then we're going to have no solution. And since we have no solution, the classification that we have is inconsistent. So when you're doing your homework, my expectation is that you don't necessarily have to solve or graph your your two equations if they're no solution or they're infinitely many. If they show up as an intersection, you must graph it in order to solve the system and then prove it algebraically. Last thing I have is a story problem. It says a soccer league offers two options for membership plans. Option A includes an initial fee of $40 and costs $5 for each game played. Option B costs $10 for each game played. I want to know after how many games will the total cost of the two options be the same. So I need to write two equations. I need to write one for option A, and then I need to write one for option B. So option A says that I'm going to have some value y, which is the total cost, whatever it may be. It says it's $5 per game, so I don't know how many games it is, so I'm going to put that as x, but there is an initial fee of $40. Option B has a total cost, but all it is $10 per game. I don't know how many it is, but that's there's no initial fee towards it. So X determines how many games are played, and then Y is the total cost. Now, what can be an issue, especially when you're doing graphing, when it deals with a much larger scale, because like see here, our y-intercept is 40, and then B, our y-intercept is 0. So there is a lot of chances for human error. You know, even I, when I graph this, would be, probably wouldn't get the correct answer right away. But there's a way that you can prove it by making a t-chart. So I'm going to make a t-chart with x and y for option A and x and y for option B. And what I'm going to do is I'm going to place values in for, I'm going to put one, I'm going to go 1 to 10. And I'm going to do the same here. And so what I'm going to do is I want to find out what when x is 1, what my y is for option A. And when that happens to be 45, if it's 2, it's 50, 3, 55, 4, 60, 5, 65, 6, 70, 7, 75, 8 is 80, 9 is 85, 9 is 90. So now for option B, if my x is 1, my y is 10. I got 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay? Now, what I want you to pay attention to is, see how I have an eighth and an 80 and an eighth and an 80 that are exactly the same? That means that that is where my line would intersect. My line would intersect at coordinate 8, comma 80. So going back to the question, it's asking after how many games will the total cost of the two options be the same? I can say from that t-chart it's going to be 8 games. And that is solving systems of linear equations by graphing. Hope this helps. Until next time.